we introduce Trace, a one-stage method that regresses multiple 3D people and their global trajectories from a video captured by a dynamic camera. Most existing methods estimate human bodies in camera coordinates. Given the input video, Trace tracks the subjects presented in the first frame through time and recovers their global trajectories. It does so in one shot. Trace consists of 4 subparts: monocular 3D detection, monocular 3D human pose and shape estimation, tracking, and recovering their global trajectories. To address these problems using a one-stage framework that is trained end-to-end, we introduce a novel 5D representation. 5D here includes 3D space, identity, and time. We also collect a new dataset to support the in-the-wild global trajectory reasoning. In conclusion, we introduce a one-stage method for reasoning about 3D people, along with their temporal trajectory and identity in global coordinates. This task is very challenging for 2 main reasons. First, in a video captured by a dynamic camera, the motion of the camera and the bodies are coupled. This makes it hard to estimate the global human trajectory and disentangle it from camera motion. Second, occlusions often happen in daily videos, making tracking difficult. To address these problems, Trace first extracts temporal features and then decodes each subtask with a separate head network. First, via 2 parallel backbones, Trace encodes the video and its motion into temporal image feature maps and motion feature maps. The detection and tracking branches take these features and perform multi-subject tracking to recover the 3D human trajectory in camera coordinates. Specifically, the detection head estimates the 3D positions and confidence of all people in each frame. The tracking branch estimates the 3D motion offset map, indicating the 3D position change of each subject from the previous frame to the current frame. From the estimated 3D detections and 3D motion offsets, a memory unit determines the subject identities and builds human trajectories in camera coordinates. The mesh branch regresses all the human mesh parameters in simple format from the temporal feature maps. Finally, to estimate subject trajectories in global coordinates, the world branch estimates a world motion map, representing the 3D orientation and 3D translation offset of the subjects in global coordinates. Starting with the 3D position of the subjects in the first frame in camera coordinates, we accumulate the 3D translation offsets to obtain the 3D trajectory in global coordinates. To support the in-the-wild global trajectory reasoning, we collect a new dataset named Dynacam. We simulate a moving camera using videos captured by static cameras. To simulate a rotating camera, we project panoramic video frames into regular perspective views. To simulate the 3D translation of dynamic cameras, we use a sliding window to crop regular videos captured by a static camera. Then, we generate pseudo-ground truth 3D human annotations via fitting simple to detected 2D pose sequences. With pseudo-human poses and camera pose annotations, we obtain the global human trajectories using the PNP algorithm. We consider 2 baseline solutions for comparison. The first uses BEV to regress the 3D position of people in camera coordinates. We then estimate the camera poses using a SLAM method, DPVO, to convert the results to world coordinates. However, when the input video contains moving subjects, it is hard for SLAM methods to reliably estimate the camera. The second baseline method is the recent state-of-the-art method, Glamour. Glamour infers the global human trajectory from the local 3D poses, but does not take scene-related information into account. Glamour ignores scene-related information, which makes it fail in common scenarios, like riding a motorbike. We also compare our method with 2 recent methods for tracking under occlusion. To handle occlusions, ByteTrack employs a Kalman filter that acts as a temporal prior and aids multi-object association. Such handcrafted priors are vulnerable to irregular motions in videos captured by dynamic cameras. To track 3 people over time, PAP assembles separately extracted 3D cues for tracking, including 3D appearance, 3D poses, and 3D locations. However, without end-to-end learning of temporal cues, PAP suffers from failures under severe occlusions. Therefore, we propose to model both the scene and human motions with our novel 5D representation to holistically exploit all temporal cues in an end-to-end manner. By learning a holistic 5D representation, Trace avoids imposing handcrafted priors for tracking and can adapt to more general cases with irregular human motions. Going beyond the 3D cues used by PAP, end-to-end learning in 5D makes Trace more robust to occlusions during tracking. With a holistic 5D view of both human motions and scenes, Trace can handle more challenging cases. Since Trace sees the whole scene, it can use information about the scene motion to avoid Glamour's failures caused by inferring global trajectories from local 3D poses only. Here, we provide qualitative comparisons between Trace, PAP, and Glamour. Notice that when there is person-person occlusion, PAP loses tracks while Trace is able to maintain the subject identities. Under long occlusions, PAP identifies people as new people when they reappear. This is illustrated by the changing color of the person. Note how Trace maintains persistent tracks through long occlusions. Glamour can't perceive scene-related motion, while Trace can. Trace performs better in handling complex trajectories. Note that when the human motion state changes rapidly, Trace still produces reasonable estimates. We also report some failure cases that illustrate the limitations of Trace. Currently, global trajectory estimation can be disrupted by occlusion. Dynacam doesn't contain sequences with translation into and out of the scene. For this, we need training data that includes 3D human poses in 3D scenes with ground truth. Here are some qualitative results on internet videos. In conclusion, we introduce a one-stage method for reasoning about 3D people, along with their temporal trajectory and identity in global coordinates. To do so, we leverage a novel 5D representation. We introduce two novel motion offset representations to explicitly model temporal multi-subject association and global human trajectories from temporal clues. This enables our network, Trace, to be trained in an end-to-end manner. Trace estimates global human motions and trajectories in global coordinates, achieving state-of-the-art results. Thanks for watching.